So today I'm going to take a bit of a break from teaching Java and teach a little bit of data structures. The most basic data structure you should know is how to store a list of things. And there's actually two different ways to store lists of things, or, there's an infinite number of ways, but there's two basic ones that come up all the time. And the obvious way is arrays. You can store a list of things in an array. And the other one is linked lists, which you've probably seen before. And if you've used a language like Scheme or Lisp, then those languages are based on lists. They have lists built right into the language as the basic operator that you're always working with. I'm going to talk a little bit about array-based lists for a few minutes, but those are pretty easy, so those won't take long. Then I'm going to spend most of the lecture on linked lists. So, array-based lists. This is the obvious thing to do. If you want a list of things, then you allocate an array big enough to hold all the things you want to list. And there's a big advantage to using arrays, which is that it gives you very fast access to any particular item. Specifically, if I want to find, say, the 2 billionth item in my 5 billion item list, I can find that item in a very tiny constant amount of time. So that's the great advantage of arrays. But arrays have some pretty big disadvantages as a way of storing lists as well. Let's look in particular at two disadvantages that are going to motivate not only lists, but a lot of other data structures we'll learn this semester. The first one is, suppose we want to insert an item, not at the end of a list, but at the beginning of the list. Or even in the middle of the list. It doesn't have to be the beginning. Almost everywhere is expensive. Then how long does it take? Well, what we're going to have to do is take all the items that come after the item we're inserting and slide them over one spot to the right. And so that's going to take time proportional to the length of the list. So let me show you what that means by showing you code that actually does that. So here's a list class, public class list, and the list is going to be stored in this array called A. To keep things simple, I'm just using a list of integers for now. And so here's a constructor that constructs an empty list. So what this does is it takes the field A inside the list class, makes it point to a new array of 10 ints. And that's just an arbitrary choice that we start with 10. We don't know necessarily how long the list is going to need to be when we first construct it. So we make some space, and if we need more later, we'll add more later. And the list object also has a field called last item, which is initially set to -1 when you construct an empty list. But the idea here is that when we start adding items into the list from left to right, then last item is going to tell us what is the last valid item that we're actually using. And so later on, the way you'll store a list of 2 items, for instance, is that you'll set last item to 1, and that's going to mean that the last array index that actually holds a useful item is array index 1. And all the array indices after index 1 don't store anything yet. So now we want to insert things into this list, and so I've written a method here called insertItem whose job is to do that. And so the issue here is, let's suppose that you have a list that looks like this. And you want to insert another item, let's say the number 9, and you want to insert it right here where the 2 is. You want it to be the second item in your list. Then what's going to happen is that before you can put the 9 there, the 2 has to shuffle over a space to the left. But there's no room for the 2 until you move the 3, and there's no room for the 3 until you move the 4, and so on. So what happens is you go through the list from the end backwards, shuffling the items over, and then you have room for the 9. And that is how you insert an item into an array-based list. And so here you can see the code that does that shuffling, and then inserts the new item. And you can also see that it takes a long time. If there's a billion items in that list, then it takes a billion microseconds or whatever to insert just one item into the list. Question? Uh-huh. And that is the second disadvantage of array-based lists. Yes. So I'll talk about how to address that now. So I've just shown you one advantage, and the gentleman in the back pointed out a second, I've just shown you one disadvantage. The gentleman in the back pointed out a second disadvantage, which is that an array has a fixed length. Now, that's fine if you know in advance that your list, say, is never going to have more than 100 items. You just allocate 100 items. If you don't know how long your list is going to be, and it might grow and grow and grow and grow, then you have to think a little harder. You could allocate 1 billion items, but then all the other processes on your machine might not have memory. You may be wasting a lot of memory. So instead, what we do is we actually sometimes have to resize the list. And so to take that into account, we now have to add this new chunk of code here in this box to the middle of the insert item method, in addition to what we already had. What does this new piece of code do? Well, suppose that your array is full and you want to add another item. Well, this piece of code, you can see this line here, allocates a new array called B, and this new array is going to be bigger than the array we were using before. We look at the length of our current array, a.length. We multiply it by 2. This is a somewhat arbitrary decision, but our rule is every time we run out of room in our array, we're going to double the size of the array. And the reason we want to double it is so that we don't have to do this resizing too often. You definitely do not want to have to resize the array every time it grows by 1 item. So to make sure that we'll have plenty of room for expansion, we double the size of the array. So now we have an array with twice as many entries. And then we have to go and copy all the items from the old array to the new array, which is obviously expensive if your array is big. But then we have room to add as many items again, so in the long run it balances out. And one other thing I want to point to here is how we replace the old array with the new array. I just have to write A equals B, and what that does is it throws away the old array and installs a new array that's twice as long to replace the old array. But we can only do that because we've copied all the items from the old array to the new one. So, any questions about that? Mm-hmm.
So basically, after we copy the whole list, then we insert, right?
After you've copied the whole list, then you can insert. That's correct.
But can we
If you're clever, you can write code that does them both simultaneously and makes it a little faster. Yes, you can. Mm-hmm.
First, we initialize last item to be -1, right? So now it's checking if the length is 0.
So you're talking about this condition here? Mm-hmm. Well, let's look at this array right here. Just before I need to resize the array, last item is going to have a value of 3. Because this is an array of length 4. It's full. That means the last index that has a useful item is index 3. And so now we are this comparison basically says, is 3 plus 1 equal to 4, the length of the array? And it is, so that's how we know that we have to resize now. Does that answer your question? Okay. Other questions? So that's everything I have to say about array-based lists. From here on, I want to go on to linked lists, which are going to take a lot more time to explain than array-based lists. One thing that's interesting about linked lists is that they're what's called a recursive data type, meaning that they reference themselves, or it's a type that has references to its own type. We'll see what that means in a second. But first, a quick description of what's going on here. A linked list is made up of what are called nodes. And a node basically has two components. First of all, each node stores one of the items in the list. And the second thing that's stored in every node is a reference to the next node in the list. For those of you who have been exposed to Scheme or Lisp, these two things are just like car and cdr. So in Scheme or Lisp, car is what tells you what item is stored in a list node, and cdr is what tells you how to get to the next node in the list, so you can read the next item. I'm going to now define a class that stores these two fields. And I'll call it a list node. And for now, our items will still be integers, just to keep things simple. And every list node is going to have a field called next that points to the next list node in the list. Now, this is what I mean when I say that linked lists are a recursive data type. You'll notice that here in this declaration of the next field, I have a field of type list node. And the reason that's interesting is I'm declaring a reference to a list node when I haven't even finished defining what a list node is yet. And so that's what makes the data type recursive. It can point to itself, and yes, we can start talking about list node fields even before we finish defining what a list node is. Which is kind of cool. So now that we've got this class, let's make some objects. Let's make some list nodes of this class and hook them together. So imagine that the following code is in some other method. I'm not going to write the method declaration. I'm just going to start writing code. Oops, forgot some parentheses here. All right, so there in one line of code is a declaration that declares 3 different list node variables and constructs 3 different list nodes. And I want to put some items, some integers, into those list nodes. So all right, I'm going to draw what we've got so far here. We've got a list node object with an item of 7. And its next field at the moment has not been initialized yet, or at least not initialized by us. So that's going to be a null in that box, yes?
Why were you able to assign 7 to L1 without saying L1.item?
Oh, did I blow it? I'm sorry, I blew it. All right, thank you. So these lines of code, now that we've got it right, will again construct 3 list node objects. And we set the item field of the second one to 0. I'm deliberately leaving some space between the second one and the third one that we'll use later. So now that we've got these 3 list nodes, I'm going to write some more code to link them together. So let's make L1 point to L2 by writing L1.next equals L2. And continuing in this vein, we'll hook L2 so it points at L3. And so these lines of code hook these together into a list. And I want L3 to be the last node in the list, so it's not going to point to anything. Its next pointer by default is already set to null, but I'm going to make it explicit just so that there's no ambiguity. I'm going to write L3.next equals null. And recall, I draw an X in that box as my way of indicating that's a null pointer. Couple of comments here. One thing is that null is a Java keyword. So the word null in Java is reserved for null pointers and can be used only for that. And second point is that here, technically that last line of code was not necessary in Java, but if you're writing in C or C++, that last line of code is necessary, because C and C++ do not automatically initialize your memory for you. They just leave whatever random bits happen to be lying around in that piece of memory when you allocated it, and that could be complete garbage. So it is good to get into the habit of not assuming that all your fields will be initialized for you by Java, even though they are, and get in the habit of explicitly giving them assignments, because someday, sooner or later, you're probably going to have to write code in C or C++, and the kind of bugs you get when you forget to initialize memory are really hard to find. So it's better to get in a good habit now of always initializing your own memory, regardless of whether or not Java does it for you. So the next thing I want to do is I want to simplify the programming a little bit by adding a few constructors that will help me shorten this code a little bit. So I'm going to have a list node constructor that initializes the two fields as part of the parameters. Because I can use this to help me shorten the code when I'm writing big lists and putting a lot of list nodes together. And I also want to have one for the node that goes at the end of the list. So I'm going to have a special list node constructor just for the last node in the list. So now that I have these two constructors, I can use them to emulate the const operation in Scheme and Lisp. And thus, I can construct the same list that I just constructed with one line of code. Like that. So that one line of code kind of replaces all the previous lines of code, except that it doesn't set up the references L2 and L3. It gives you the same list, but it only sets up one reference to L1. Yes?
Why do we need a separate constructor for the last element? I mean, why can't we just pass null to the first?
You could just pass null to the first constructor instead of using the second constructor. Sure. So then this would say 6 comma null. But I just wanted to make things as short as possible because I'm lazy. So I write these constructors once, and then I can make lists like this. If I'm making like 1,000,000 lists, then I do a lot less typing. Other questions? All right, so now that we got these linked lists defined, let me just point out some advantages and one disadvantage. So, the advantages of linked lists as compared to array-based lists. So now you can insert something into the middle or beginning of a linked list much faster if you have a reference to the place where you want to insert the thing. In fact, it takes a small constant amount of time to insert a new node into the middle of a linked list. But again, there is an important caveat here. This is only true if you have a reference to the node right before the spot where you want to insert the list node. So sometimes that's a big if, but there are a lot of situations where that's true and we can do that. And the second advantage of a linked list is that it's easier to resize. I mean, it automatically resizes itself every time you add a new node to the list. So the list can just keep growing until the memory runs out. And you never have to stop and create a whole new array list and copy all the items from the old one to the new one. You never have to have a long delay just to insert one item into a list like you sometimes do with arrays. All right, so what I want to do is, with this, write a little bit of code to insert a new item into a list immediately after this node. Where's a good place to do that? No, I'll have to put the code here. All right, so again, this inserts a new item at a designated place, namely this place, in a linked list. So it's a pretty simple method, one line of code inside the method, basically. It's called insert after. The reason it's called insert after is because it inserts something after this list node. So it assumes that you are passing in a list node implicitly as this, and we're going to hook up a new list node after this list node by creating that new list node, putting the item into it, replacing its, giving it the same next pointer as this list node, and then changing this list node's next pointer. So even though this is one line of code, you have to think about it a little carefully to understand it, because the word next appears here twice. And those two nexts, they're not quite the same. So remember that Java has maybe a slightly non-intuitive order of executing things, where usually execution flows sort of from the right side of the line to the left side of the line. So the first thing that Java does when it executes this line of code is it looks at what item is, and it looks at what next is in this list node. And so you are getting here the old value of next. And the reason I say the old value is because we're about to change it. And then we construct a list node that has copies of these two fields with new list node. And then the last thing we do is we assign a reference to that list node into this.next. So this is going to be a new value of next that gets written and replaces the old one. Now the old one is stored in a different node. So simple line of code, but a lot going on. Let's look at this actually acting on the list we had here before. And the line of code that I'm going to execute here now is L2 dot insert after three. So we've got this line of code. What does it do? First of all, we pass in this parameter 3, and the code is going to construct, well, let me point out that when we call insert after, there's a local variable called this. And this points to the same thing as L2. Java has just copied the reference in L2 up into a box called this, which exists inside the insert after method. And now the first thing insert after does is it constructs a brand new list node, and it sets the item to 3 because the parameter was 3. So that gets copied there. And the next field is going to be copied from the box this dot next. So here's this dot next in this box. We're going to copy the contents of that box into the new list node that we're constructing. So that new list node is going to point to the same list node that L2.next points to. After that reference gets copied, then the value of next gets replaced because we assign it to point to the new list node. And it's important that all those things are done in the right order because you don't want to put the wrong version of next into the wrong box. And now you can see we're done. We have, once again, a linked list where we've stuck a new node in between two other nodes. Are there any questions about that? Mm-hmm. Right, so we have created a new node that does not have any variable referencing it. We can create a variable called L4 that points to that node afterwards in the main program if we want to, by just setting it to L2.next right after we call insert after. Mm-hmm. So what is passed in implicitly is when you call L2.insert after, that means this variable here, L2, is implicitly copied into a box called this in the insert after method. Does that answer your question? Okay, cool. Mm-hmm.
We've been talking about linked lists here. This is all user defined. Is there like a built-in linked list class in Java, or?
Java definitely has a built-in linked list class, including one called linked list. It probably has multiple ones. The library is so big I don't know it all, but at least one. Mm-hmm. And just as a reminder, 61B, as I teach it, is meant to teach you the internals of data structures, which is why I want you to implement your own in this class rather than using the ones in the Java library. But when you go into future classes later in your CS career, you'll probably want to start using the data structures in the Java library, just hopefully that by then you'll understand how they work and why they're slow, or why they're fast when they are fast. All right, so I just told you some advantages of linked lists, and there's an important disadvantage too that you really got to know about compared to arrays, which is suppose that you want to do something like finding the nth item of a linked list. Well, unfortunately, usually that's pretty slow. If you want the nth item in a linked list, pretty much what you usually have to do is start at the head and then follow the next reference n-1 times. If n is a billion, that's how long it's going to take. So that's slow. And as we compare these different advantages and disadvantages of array-based lists versus linked lists, I want to say that one of the points of the data structures part of this course is going to be to try to mediate a compromise between these two different sets of disadvantages. We're going to be looking at data structures such as balanced binary trees that allow you to do all these kinds of operations reasonably quickly and not have the big disadvantages and the big slow operations. But before we get there, we have to master lists and learn more Java. So before we go into the next part, I want to just quickly change our lists. So far, I've just been using lists of ints for simplicity, but now I want to use lists of objects. And we can make lists that reference any kind of Java object, not just one class of Java objects. And the way we do that is with the object keyword. So just one little change here. Item is not an int anymore. Item is now of type object with a capital O. So technically, object is not actually a Java keyword. It's just the class in Java that envelops all other classes. So every object you declare in Java is a specialized class of the object class. So you can store any kind of Java object in this item field, regardless of what it is. You can't store primitive types there, but you can store any class of object. And I've made one other change, which is that I now have an S here. S stands for singly linked list. And we're going to learn doubly linked lists shortly, so you'll see what that means by comparison with doubly linked lists. And you'll also see a lot of S-list nodes in this week's lab and homework. All right, now that we've got this list class, these lists of objects defined, I want to define a list class as well, which is going to be separate from the list node class. And I want to motivate why we want to do that. So let me tell you a few problems with representing lists just as list nodes. So it's not that S-list nodes are bad, it's just that by themselves, they can't do everything that they ought to be able to do. And here's the way to think about this. Problem number one. Suppose that you have two different pointers, X and Y, that are both pointers to the same shopping list. So let's draw that like this. We have a list node, and my object field points to the string milk. So that's a shopping list with one item. And I have several references to that S-list node. This reference is maybe you, our X, and this other reference, Y, is maybe your roommate. Now, suppose that you want to insert a new item at your shopping list because you just remembered you're out of soap. So you want to insert a new item at the beginning of the list, and it's very easy to write code to do that. Here it is. Set X equal to, well, let's create a new list node. And my S-list node will store the string soap as its item. And we don't want to lose the rest of the list, so we'll set the next field to X. So what does this do? This creates a new slist node. That points to the SOAP. We copy whatever is in this box X into the next field of that slist node. So now that next field points to the same slist node that X points to. And then finally, this line of code now stores a reference to that new object in X. So that means that this gets erased and replaced with this pointer. So now X has a list with two items in it, soap and milk. What's wrong with this? Well, now if your roommate goes shopping for groceries, he'll forget to buy the soap. Because why? Your roommate's list still points just to the milk. This is not desirable. When you add something to a list, you want everyone who's got a pointer to that list to see the changes. So that's a problem. Second problem, how do you represent an empty list? Well, the obvious way to represent an empty list would be just to set your pointer to null. So if I say X equals null, I think I have an empty list there. The problem is, what if I try to call a slist node method on X? So I want to insert something after X, for instance. Well, if you do that when X is null, you get a runtime error. That means your code will compile fine, but when you actually go to run it, it throws a null pointer exception. Why is that? You just can't call methods on null. So if X is null, when you say X dot anything, you get a null pointer exception. You just cannot do null dot anything in Java. Always gives you an error. And you might say, well, X is of type slist node. Why can't Java just call insert after on that null and set this equal to null? And what's wrong with that? And there are good reasons why Java will not call a method on a null pointer, even if you know the right type of the pointer. And those good reasons, I can't explain them until we talk about inheritance later in the class. But if you want to look ahead, Google dynamic method lookup and you'll find out why this is a no-go. So here we've got two problems. And I want to solve both these problems. And the way I'm going to solve them is by having a separate class for singly linked lists, which I will call slist. And the job of the slist class, its main job, is just to maintain the first node of the list, which we call the head. And that's pretty much all the slist class needs to do, but that all by itself solves both these problems. We will also have just for convenience, we will also have the slist class store the size of the list as well. So here's some code for that. So I've got this class called slist. And its main job is to store the head of the list, whichever slist node is at the front. And if it's an empty list, then head can be set to null. But the slist itself is never set to null. There's always an slist, even if the list is empty. There's an slist object. Just for bonus, we also store the size of the list, Because if you don't store the size of the list and you want to know the size, you have to walk through the entire list and count all the nodes. That's slow. Instead, we're just going to keep a running total of how many list nodes there are every time we create or delete a list node. And that way, when we need to look up the size, we can do it fast. And so the slist constructor for an empty slist just gives you an object whose head is null and size is 0. So that's what the constructor gives you. One slist object. And where things get interesting is now this insert front method can be written in such a way that it solves the problems that the other problem, the first problem I told you about, that you and your roommate want to have the same grocery list. So the way we resolve that problem is now there's this slist object. And if, let's suppose there's one thing in your list, and the head of your list points to, I'm leaving a big space in here for future use. The slist head points to this slist object, whose item is milk, and whose next field is null. And that's what a list looks like when it has one item in it. And now you, X, have a reference to this slist object, and your roommate, Y, has a reference to the same slist object. And when we run insert front, so this method here, we're going to run it now by calling insert front fish. And when that line of code executes and calls this method, then what that method does is it constructs a new slist node, sets the item to fish, sets the next field to point to the head. So see here we're passing in the head of the list as the next field of this new node we're creating. So the head gets copied into this box here. And now that we've constructed that new node, now we can fix the head of the list to point to the new first item in the list. And we update the size so that it's now 2 instead of 1. And you'll notice that now we're happy because when your roommate goes to buy groceries, they won't forget the fish. Any questions about that? Mm-hmm. The size should not be static because every list has a different size. Other questions? Mm-hmm. Say that again. The list itself should be static? You don't want every list to have the same items. You want different lists to have different items. In this example, we want X and Y to know the same items, but we do that by having X and Y point to the same list object. We don't want to have different list objects having the same list. Mm-hmm. What's the purpose of size? The purpose of size is sometimes you want to look up the size of a data structure without having to go through it and count every item. And if you do that frequently, then it's faster to just keep a running total of how many items there are in your list instead of having to count them every time somebody asks you how many there are. All right, we have time for a quick break, so I'm going to, let's see, how long shall I? We will have a 5-minute and 17-second break, which will be over when the music ends.
Boys Club. Where the boys are. Boys Club. Where the boys are. Oh yeah. Boys Club.
So far, we've usually declared fields and methods using the public keyword, but on the other hand, sometimes we want to declare them private. A private method or field is one that's both invisible and inaccessible to other classes. And can only be used within the class in which that field or method is declared. You'll notice that I said it's inaccessible to other classes. I did not say to other objects. Hopefully most of you figured out during homework 2 that the date class, for instance, has private fields, but when you call a method on one date object, it has access to those fields in all the date objects. And that allows you to do things like compute the difference between two different dates. So, again, a date method can access the private methods and fields in any date object, not just this. But another question is, why would you want to have private fields or methods? And it's all about software engineering, and in particular, it's all about how do you design different modules so that they can work together and be easy to change without destroying the functionality of your program. So, with that in mind, one reason is we want to be able to prevent data within an object from being corrupted by other classes. And a second reason to do it is you want to be able to design classes so that other classes do not depend too much on how you implemented your class. And the reason you want to do that is because you want to maintain the freedom to change your class, to change its implementation later on without causing other people's programs to fail. So again, it gives you freedom later on to improve the implementation of your class. Without causing other classes that depend on it to fail. I want to give you an example of code that shows what private actually does. So, here I have a date class, and I've declared two of its fields private, the day and month, so that other classes can't come in and change my dates. And I also have, just as a demonstration, a private method called setMonth that allows me in my class to change the month and a date, but doesn't allow other classes to just go in and change the month willy-nilly. And here's a date constructor, and you guys know how to write one of these now. This constructor is public, but it has lots of error checking code to make sure that nobody can construct an invalid date like November 31st. All right, so let's suppose that we have that code written by Dudley Do-Right, and now we've got a different class down here that written by Dudley's coworker at Google, Snidely Whiplash. And this class is called Evil Temperer, and its goal is to try to destroy dates and make them invalid. So what Snidely does is constructs a date and then tries to set d.day equal to 100 and mess up the date, but day is a private field. And so when you're outside of the date class, you not only can't change it, you can't even read it or know it exists. So Snidely's plan is foiled. And likewise, the same goes for private methods. When you have a private method like setMonth and you try to call it from another class, you can't. So Java, it stops you from this because Java won't even let you compile this code. You will get a compile time error when you try to compile the code because the date class has declared its vulnerable parts as private. And we prefer it that way. Question? I'm sorry, can you talk a lot louder, please? They might or they might not. The question is, do the private fields have getter and setter methods that allow you to read or change those fields? And often they do. In the case of a date class, you would definitely want getter fields. You might want setter fields. But the bottom line answer is it's up to you. You get to decide what your date class is supposed to do and what it's not supposed to provide. And it's all your decision. Mm-hmm. Fields by default are neither public nor private. As the next few week or two goes on, we're going to learn that there's actually 4 different kinds of protection in Java. 2 of them are between public and private, and one of those is the default. We don't yet know enough about Java to understand those other 2 kinds of protection, but be aware that once we have enough background to understand them, we'll learn that there are 2 other kinds of protection between public and private, and one of those is the default, if you don't use a keyword like public or private. Question here. Is it better to have getters and setters, or is it better to have what? Oh, public fields. That totally depends on whether or not there are invariants you want to enforce, and I will talk about invariants next, so that you'll be able to understand that answer. Question in the back. Louder, please. Why do I make a public class? If I want other people to be able to use my dates, then it makes sense to make it public. There is an alternative to public classes, but we're not ready to talk about that yet. We'll learn about that when we learn about packages. Question? What if evil temper inherits from date? A private field is really private even to subclasses. So evil temper still can't read the date if it inherits date. But that is a prelude to one of the other kinds of protection we'll learn about in a week or two. So now I want to give you some definitions of terms we want to understand that are related to software engineering. So our first software engineering concepts. Every class has what's called an interface, which is how other classes are supposed to interact with your class. And the interface consists of the prototypes for all the public methods, and sometimes also for public fields, And in addition to that, you include a description of the behaviors of those methods. So that the user who wants to use your date class can figure out how to use your date class and what each of the methods is supposed to do from a human understandable point of view. And what's interesting is that the interface consists of these two things, but they're expressed in different ways because the prototypes are Java code, whereas the descriptions of their behaviors are generally written in plain English because this is the part that's supposed to explain to the human how to call your class. And you want that description to be as clear and readable as possible so that people who want to use your class will understand how to use it. So this leads to the idea of we want to create data structures. When it's possible, we want to package those data structures in a nice way so that we can call them an abstract data type. And so an abstract data type is a class that has a well-defined interface. But the implementation details of your data structure are hidden from other classes. So what does that mean? That means I would like to have an interface for lists that lets me do things like find the nth item in a list, add a new item to the beginning of a list, delete an item from the end of a list, insert an item in the middle of the list at position X. But the interface doesn't reveal whether I'm using an array-based list or a linked list. In fact, I could be using array-based list code one day, and the next day I could replace it with linked list code, and the person who's using my lists would never know that I had changed from one data structure to another. So the interface is supposed to expose how you interact with me, what my list can do for you, and how you add things to the list, remove things from the list, etc. But it does not expose whether I'm using arrays or linked lists or balanced binary search trees or some completely different data structure. That is hidden, and that gives me the power to replace a slow implementation with a fast implementation, replace a buggy implementation with a one that works better. Yes? Well, you can always give somebody .class files. But the other thing is, if you give them source code, but you tell them, don't change my source code or I no longer guarantee that my next version of lists will work with your software, then encapsulation like this kind of abstract data type still works because you have declared your fields private, so they cannot write their implementation so that it depends on how your implementation is done. You can change your implementation, and their code will still work as long as their code only goes through your interface. We're going to implement a lot of abstract data types this semester. Generally, one of the things that distinguishes abstract data types from just random repositories of data is that they have invariants. An invariant has everything to do with the implementation of a data structure, not its interface. So this is one of the things that's hidden by an ADT. But an invariant is something that is always true, assuming that your code is free of bugs. For example, the date abstract data type enforces the invariant that any date object always stores a valid date. Okay, so that's an invariant in quotes. A date object always stores a valid date. No November 31st, ever. And one way that invariants are enforced, not the only way, but certainly the most important way, is by allowing access only through method calls. So other classes cannot create November 31st because they can't change the day directly, and your methods do error checking to make sure they never create a November 31st. And so somebody asked earlier the question, when should you declare methods private and use getters and setters versus when should you declare something public? And the answer is, do you have any invariants that you should enforce? If you don't have any invariants, if you just have an object whose sole purpose is to pass along data and any data will do and there's no restrictions on what that data can be, then you can just use public fields. You don't need to do anything fancy. But if you have an invariant you want to enforce, then you should encapsulate your data structure as an abstract data type and use getters and setters where necessary to ensure that it's impossible to violate an invariant. So, as I just implied, not all classes are abstract data types or need to be encapsulated in this way. Some classes are just nothing more than data storage units. And importantly, have no invariants. And in that case, fields can probably be public and you're fine. But when you have an invariant to enforce, then you need to use private fields to enforce that invariant. Any questions about that? So now that we've got this idea, I want to talk about what kinds of invariants we might want to enforce on S-lists. So let's think of S-list as being an abstract data type now. So I told you before two advantages of S-lists, that they solve two problems we had: how to store an empty S-list, how to put a new item in your shopping list and make sure your roommate will see the change. There's another advantage, a third advantage of the S-list class now. Which is it can enforce invariants. And I'm going to list two invariants that probably suffice. As long as you write your S-list code well and have no bugs, you can enforce these two invariants. So invariant 1 is, since we have this size field, I would like to enforce the invariant that it's always correct. Another way of saying this is the short way of saying it. The long way of saying it is, I guess the short way of saying it should be correct too. The long way of saying it is, I want the size field to always be equal to the number of S-list nodes I can reach by starting at the head of the list and following next pointers. So that's my first invariant. A second invariant is something you might not have thought of, but I really want to make sure my S-lists are never circularly linked. And what do I mean by that? Well, imagine a list that goes like this. So as far as I'm concerned, this is a defective S-list. We don't want to allow anyone to create an S-list with a loop in it. There should always be a tail node that's equal to null, or always a tail node is defined to be the node in your list whose next reference is null. There should always be a tail node. Now, both these goals can be accomplished as long as we implement S-list right. Because only the methods of the S-list class can change the S-list's internal fields. Nobody else can change them. And you can write your methods in a way such that they always enforce these invariants, assuming that they were already satisfied. How does S-list ensure this? By two means. First of all, we make the S-list fields private. Specifically head and size. And secondly, what I'm about to tell you is not the only way to enforce these invariants. We'll see different ways later in the semester. But one thing that makes life easier is if you never give somebody access to any of your S-list nodes. So no method of the S-list class, as we're going to see it this week, ever returns an S-list node. Mind you, we're going to change this in a week or two, which will make it harder to encapsulate things. But just since we're to get started here, if you don't give somebody a reference to any of the S-list nodes in any of your lists, then nobody can muck with it. And so these two facts, both of these two facts are necessary or help you to enforce invariant 1 and to enforce invariant 2. And think about why. In particular, an evil tamperer can't just go into your list and create a loop like that, or truncate your list by setting one of the next fields to null in the middle of the list, or some other vandalism like that, because of these two things that we're enforcing. And when you do this, you're not just defending your S-list from evil tamperers, you're also creating security for the person who's using your lists, that they never have to worry about these things as bugs. They never have to worry that something they do might accidentally create a bug where the loop gets circularly linked or the loop gets truncated, because you've designed the S-list class so that that can never happen. And that helps the person who's using your slist class because it reduces the space of possible bugs that they might have to look for if their code using your slists doesn't work. Any questions about this? Yeah. In this case, no, there's going to be no get vector for head. The whole point is we don't want to let people play with our list nodes. So now let's talk about doubly linked lists. So, as we've seen, inserting an item at the front of a linked list is pretty easy. So is deleting one. But inserting or deleting an item at the end of a list takes a long time. Why? Well, because you have to start at the head of the list. You have to go next, 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 next until you get to the end of the list, and then you can do something with the end of the list. That takes a while if the list is big. So here we're going to do what's called a doubly linked list, which has two changes. First, we're always going to keep a reference to the tail of the list, not just the head, the tail being the last node in the list. And second of all, now we're going to have list nodes pointing in both directions. So every list node knows the next node in the list and the previous node in the list. So when you're walking through a list, you can walk both ways. So I'm going to call this class dListNode for doubly linked list. And just like singly linked lists, it'll store an item and have a next field. And now I'm adding a previous field as well. And for the same reason I wanted to have an slist class, I want to have a dlist class too. And this will store the head. But it will also store the tail, the last node in the list. And why not have a size as well? So there's my list class, two different classes that together help me build lists, the dlist nodes and the dlists. And here's what a typical doubly linked list might look like. Got the head of my list. The head of the list always has a pre-field set to null and a next field that points to the next item in the list. Whose pre-field points back to the head of the list. And I'll have 3 nodes in my list so that this is the tail that we're looking at now. And since this is the last node in the list, whoops, next, not head. Since this is the last node in the list, its next field will be null. And finally, I will have a tail back there. So for convenience of drawing this picture, I have not drawn the dlist object. There is one dlist object, and it contains this head field and this tail field. And since they're very far apart, I'm not going to draw an object around them. It also contains a size field which says 3. So one of the nice things about dlists is now that I've got this, I can insert items and delete items at either the head or the tail of the list in a tiny constant amount of time. It does not matter if there are a billion items in my linked list, these operations are still super fast. And just to give you an example of what this looks like, here's code that removes the tail node from the list. So you can see what this kind of code looks like. I want to give you a caveat. This doesn't always work. It only works on items that have, it only works on lists that have at least 2 items. But I want to show you how to do this. So first, I'm going to find the new tail of the list and set its next pointer to null. So we find the second last item in the list, and we set its next pointer to null because it's the new tail. And second, now I'm going to change the tail pointer to point at the second last item in the list. So those 2 lines of code remove the tail node. Let's see how they do that. To read this code, start by reading the part that says tail.prev. These dots get processed in order from left to right. So tail.prev means we start at tail, we follow it to the prev field, and that gives us a reference, which we follow again. And now we get to .next, which brings us here. We're going to change this field by erasing the pointer that's in it now and replacing it with a null. That's what the first line of code does. So now the second last item in the list has a null next field. And then the next line of code, well, it starts off by following tail.prev again. So here's tail. We follow it to prev, and takes that reference, which points to the second last node, and copies that reference into the tail of the dlist. So now that means we overwrite this reference with a reference to the second last node. And those 2 operations have spliced the last node out of the list. The last node still has a prev pointer, but we don't care. It may be pointing to its friend, but its friend is not pointing back at it, so it's ostracized. Poor node. Wait till it gets garbage collected, then it'll really feel poor. Again, I want to emphasize that this only works if there are at least 2 items in the dlist, because there has to be a second last node for what I just wrote to work. And if you want a method that always works, even on lists of 0 and 1 item. You have to write special case code for the case where there's 0 items in the list. That code does nothing. And the special case where there's 1 item in the list, in which case you have to change the head instead of changing tail.prev.next. But I'll leave that as an exercise. I want to show you, are there any questions before I move on? Yeah. I'm sorry, can you talk a lot louder, please? The tail ends, after those 2 lines, the tail ends up pointing at the middle node. Yeah. So what I want to do is show you a trick that's a slightly different way of storing a doubly linked list that reduces the number of special cases here. It only reduces the number of special cases in this method by 1 line, or by 1 case, but it does that with a bunch of different methods that operate on the list, so it's worth knowing about. What we're going to do is we're going to have a slightly different D-list representation, again, not the one I just told you, but almost the same. And in this D-list representation, we are going to designate one D-list node to be the sentinel. A sentinel is a special node that does not represent an item. So again, let me be clear. We have 2 different D-list representations now. There's the D-list without sentinel, there's the D-list with sentinel. You can program it either way. The D-list with sentinel is slightly easier to program. So the idea of the D-list with sentinel is, here's my sentinel node. Very important, again, the sentinel should never be used to actually store an item. So the item field will, in this case, be 0 if we're using integers. If we're using objects, it'll be a null pointer. But it doesn't matter what it is because we never even look at it. We're going to have the sentinel's prev field is going to act as the tail of the list. And the sentinel's next field is going to tell you what the head of the list is, or the first item in the list. And we're not going to have a tail pointer anymore because the sentinel is doing that job. So our D-list class with sentinel does not have a tail. The D-list class will still have a reference called head, but that no longer points to the first node in the list. Instead, it points to the sentinel. So in this representation, head does not mean the first item, head means the sentinel. And here's one thing that's interesting. The head node will have a previous field that points to the sentinel. The tail node will have a next field that points to the sentinel. So our list is circularly linked. It's linked in a list. There's a circle forward. So if you start at the sentinel and you go next, 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 you get back to the sentinel. If you start at the sentinel and go prev, 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 you get back to the sentinel. There will never be a null next or prev pointer in a D-list with sentinel. And because you don't have to check for nulls, that's why you're going to have fewer special cases. So, since that's probably a little hard to read. Let me do a simpler representation here. Next pointers go in a ring forward, prev pointers go in a ring backward. That's what a D-list with Sentinel looks like. Now, a doubly linked list has a more complicated and interesting set of invariants. And these are the invariants with Sentinel. You would have different invariants if you don't use a Sentinel. But it has a more interesting set of invariants than the S-list because there's more going on. So what are the invariants we want to enforce in a D-list? First of all, there's always a Sentinel node. So the head field of a D-list is never null. It always points to a Sentinel. The second invariant is that you can't have any next fields that are null in a D-list node. And there's a symmetric one, which is that in any D-list node, I guess I said prev there, so I'll say next here. Meant to do them in the other order, but whatever. There's two symmetric invariants here. For any D-list node, the next field can never be null, and the prev field can never be null. They're always linked in a circle. There's another set of invariants that are pretty important, which are the sort of coupling invariants that if I'm holding your hand, you need to be holding my hand too. Or specifically, if x.next points to a node y, then y.prev needs to be pointing back at x. Otherwise, you have not linked your nodes correctly. And that condition also has a mirror image. It goes both ways. If x.prev is some node y, then y.next had better point back to x. And our last D-list invariant will be that the size field should be correct. And when I say correct, we do not count the Sentinel because the Sentinel does not store an item. And so it's the number of D-lists that can be accessed from the Sentinel by a sequence of next references. So again, I said before that invariants are all about how your program is implemented. These are the things that should be hidden in an abstract data type, but are really important to making sure that your code has no bugs. You want to make sure that every method you write enforces these invariants. And what that means is you can assume that when a method starts, all these invariants hold. Your job is to write the method so that they still hold at the end. Of course, if these invariants are broken when you start a method, then the method isn't really expected to be able to fix them. The idea of an invariant is if it's true at the start of a method, it's still true at the end of a method. Or actually, if they're all still true at the start of the method, then each one is still true at the end of the method. Any questions about the invariants? Yeah. Well, you have to have, the question is, if we got rid of the tail node, why can't we get rid of the head node? You have to have something that points to the sentinel, or at least something that points to one node in the list. You don't have to call it head, you could call it sentinel or something else. But you have to have some reference to a dlist node, or you've lost your list. Mm-hmm. Disadvantages to what? In here, I don't think there are any disadvantages to using a sentinel, actually. I can't think of any. Question here? What is the right command to access the size? Well, you mean from an outside class that wants to find out what the size of the list is? Well, then you write a method for that purpose. So you have some public method. You can even call it size if you want. And so this is a getter method. You don't want a setter method. The reason we keep the size field private is so nobody can change it, but we're going to let people read it by using a method. But does that answer your question? You can come talk to me afterwards if it's tricky. Yeah. Do you have to check what? You do not have to check invariance in your code necessarily. A good way of debugging a program, though, is figure out what your invariants are, write code that checks the invariants, and check them while you're debugging. And Java gives you ways of having lines of code that run only when you're debugging and not when you're actually have production code. So you can test when you want to test, and then have faster code that doesn't check invariants when you don't want to test and you just want to run fast. So with this format, people always get confused about how you would represent an empty dlist. And the answer is that in an empty dlist, the sentinel's next and prev fields point to itself. So in other words, an empty dlist looks like this. That's the list, the dlist object, and there's one dlist node object whose item really doesn't matter because we never use it, and whose next field points to itself, and whose prev field points to itself. That's an empty dlist. So now, by way of demonstrating how the Sentinel node makes it slightly less effort to write different methods, here is a complete correct method that removes the last item from a dlist in all cases. We're going to call this remove back. It removes whatever item is at the back of the list. And we only have one special case in this code, which is when the list is empty, when there are 0 items, we need to have a special case that just doesn't do anything. That's the only special case. After that, we're going to write code that works for any number of items from 1 on up. So to check for the special case, we just make sure that head.prev is not equal to head. In other words, the Sentinel does not point to itself. If it does point to itself, if those two are equal, we do nothing. If it doesn't point to itself, then these two are not equal, and we go ahead and we remove the last item from the list. And we do it like this. And if code like this isn't obvious to you how it works, you should sit down and think about it for a while, because it's important to be able to learn how to read things like head.prev.prev and understand what Java is doing when you write lines of code like that. So there's the whole method. The first line changes the tail, meaning it makes the Sentinel's prev field point at the second last node in the list. The second line makes that node point back at the Sentinel, so you've got the connection in both directions. And then we decrement the size of the list, because there's one less item in the list, and we're done. And in Homework 4 and Lab 4, which are still a week away, you'll implement more methods for the DList class. Oh, one last thing I want to let you know is that we're still working on making Project 1, but I hope it will be available sometime Friday. And so you'll have the weekend to start working on the project. And thank you.